The new section is entitled Determinants. Prior to giving a definition of determinants, we need to go over two definitions, one of which you should be familiar with, the other one probably not. A permutation on the set S equals, say, 1, 2, up to n. A permutation in that set S is a rearrangement. If S is equal to the set that just contains 1 and 2, well then the permutations would be 1, 2, and 2, 1. Maybe I won't put the curly brackets. Those are the two permutations. 1, 2, 2, 1. If S, or S prime to be different, is 1, 2, and 3, the permutations of S prime are, you can have 1 first, and then 2, 3, or 3, 2. You can have 2 first, and then 1 and 3, or 3 and then 1. Or you can have 3 first, and then 1 and 2, or then 2, 1. These are the 6 permutations on the set S prime, and these are the 2 permutations on the set S. It's just rearrangements of the elements of S. So that's a permutation. And even if you never ever heard the word permutation before, you know what it means to rearrange the letters A, B, C, or rearrange the numbers 1, 2, 3. A permutation is just a rearrangement of some set. Now we're going to talk about inversions. A permutation on the set S is said to have an inversion. Now, maybe I'll say what the set S is. They're numbers, they count their numbers from 1 to n. A permutation on set S is said to have an inversion if a larger number precedes a smaller number. And generally, we count the number of inversions. You want to count the number of inversions. Suppose you have 1, 4, 3, 2. How many inversions are there? Well, 1 is before 4, but 1's not bigger. 1 is before 3, but 1's not bigger. 1 is before 3, but 1 is before 2, but 1's not bigger. 4 is before 3, and it's bigger. 4 is before 2, and it's bigger than 2. And lastly, 3 is before 2, and 3 is bigger. So 1, 4, 3, 2 has 3 inversions. It has 3 inversions. 3, 2, 1. Well, this is going to have a lot of inversions. I suspect it's going to be 6. 4 is before 3. 4 is before 2, and it's bigger. 4 is before 1, and it's bigger than 1. 3 is before 2, and the 3 is bigger. 3 is before 1, and the 3 is bigger. And 2 is before 1, and the 2 is bigger. So yeah, there were 6 inversions. Some inversions, some permutation have an odd number of inversions, like 3. Others have an even number of inversions. 1, 2, 3, 4. 1 is before 2, 3, and 4. But 1's not bigger than any of them. 2 is before 3 and 4. 2's not bigger than any of them. And lastly, 3 is before 4, but the 3 is not bigger. This has 0 inversions, and 0 happens to be even. Generally, we want to look at the number of inversions, odd or even. Okay, we want to count the number of inversions and decide if there's an even number or an odd number. How do you tell if it's even? If it has an even number of inversions, if number of inversions is 8, an even number, then it has an even number of inversions. If our permutation has 17 inversions, 17 being odd, we would say that permutation has an odd number of inversions. Just count the number of inversions and decide if it's even or odd. Okay, now that we talked about permutations and we talked about how to count the number of inversions, now we can talk about we can now define a determinant. To talk about the determinant of a matrix, the matrix must be square. Let A be an matrix. We define the determinant of A, the determinant of A, that's what we are defining, determinant of A, which is denoted by A, with bars around it, by this definition. The determinant of A is the summation of plus minus A1 J sub 1 times A2 J sub 2 times A3 J sub 3 all the way up to AN, the n's J sub n, column JN. So I need to define a couple of things. Where we sum over J1, J2 up to Jn. Okay, so a little better. Actually, we sum over all permutations. We sum over all permutation J1, J2 up to Jn of the set 1 through n. That is, maybe that's J1, and that's J2, and that's J3, and that's J4, and that's J5. The rows don't change. The first one is the first row, the second row, the third row, eventually the nth row. But the columns change. You still have columns 1 through column n, but we keep putting the columns in different orders. We keep putting the columns in different orders. We're going to sum over all of those orderings. And now I have to tell you how to decide to use plus or minus. The plus minus is determined by the number of inversions. Even number of inversions, get the plus symbol. Odd number of inversions, get to use the minus symbols. Now, some of you may think that's a very hard-looking definition. So, let's look at it more carefully. It is possible on an exam, your instructor can tell you to calculate the determinant of this matrix by using the definition. So although later on we're going to learn shorthand techniques, calculate the determinants. Maybe for this given problem you can. Now, suppose you have a 2 by 2 matrix. Matrix A11, A12, A21, A22. You want the determinant of that matrix. That's why I put the bars. Well, since there's only 2 columns and 2 rows, it has to be square. I'm going to write A1 blank, A2 blank, 2 times. A1 blank, A2 blank. And what goes on the blanks are the permutations on 1, 2. What are they? Well, you can have 1 and then 2, or you can have 2 and then 1. Oh, and this permutation has no inversions. Even, plus. 2 is before 1, but 2 is bigger. So that inversion, that or permutation, excuse me, has 1 inversion, and 1 is negative. Sorry, 1 is odd, so we put negative. Where do we put this plus minus? That's coming right up. 1, 2 is 1 permutation of their columns. I can put 1 and then 2. And I put a plus in front of that term. Another permutation on 1, 2 is 2, 1. And that gets a minus. And there it is. That's the that is the determinant of a 2 by 2 matrix. Now, how can we see this answer a bit more clearly? Well, if you multiply those 2 numbers, you get exactly that. A11 times A22 minus, and then if you multiply those 2 numbers, you get this. That is just tic-tac-toe. It's the determinant of a 2 by 2 is that product minus that product. I know it is because I used the definition. Here's the result I got from the definition. And that's exactly what I'm saying. Multiply that diagonal minus multiply that diagonal. For example, if you have 7, 1, 3, negative 2, let's make that negative 3 and negative 7. You multiply those 2 numbers, you get 14. Minus, you multiply these 2 numbers, you get negative 3. Please don't say you wrote the negative. Get negative 3. Now, any one of you who say that this is 11 It's because you know that 14 minus 3 is 11. That would be the only reason you would write 11 down. But there's one problem. 14 minus. If the number I write here is not 3, the number I put in that box is not 3, I'll guarantee you one thing. We won't get 11. I don't care what number I put in there. If it's not 3, we won't get 11. And the number that I just wrote is not 3. It is not 3. This becomes plus and plus, and the answer is 17. So it's very, very simple to calculate the determinant of our 2 by 2 matrix. You multiply this diagonal. In this case, you get 15 minus. You multiply the other diagonal, you get negative 8. You have to know how to subtract and add sign numbers. That becomes 23. Now, what if we have a 3 by 3 matrix? What if we have a 3 by 3 matrix? So if we're going to calculate the determinant of our 3 by 3 matrix, you have to start off this way. You have to start off this way. You need to have a formula for a 3 by 3. Oh, here's this 3 by 3 matrix. A11, a general matrix. 3, A21, A22, A23, A31, A32, A33. And you want to find the determinant of this using the definition. Well, it equals to the summation of, actually let me write it down here. It equals to the summation of plus minus A1, J1, A2, J2, A3, J3. And we sum over all J1, J2s, and J3s. Well, the columns are 1, 2, and 3. There are 3 columns. What are the permutations of 1, 2, 3? Well, you can have 1 and then 2 and 3, or you can have 1 and then 3 and 2, or you can have 2 first and then 1 and 3, or 2 first and then 3 and 1. Or you can have 3 first and then 1 and 2, or 3 first and then 2 and 1. Nonetheless, these are the 6 permutations. 6 permutations. That is, I need to write down A1 blank, A2 blank, A3 blank 6 different times. I just did it once. Here is the second time. Here is the third time. The fourth time. The fifth time is coming. Here is the fifth time. And then the sixth time. The sixth time. Now, should have done this to begin with. 1, 3, 2, it has no inversions. Because 1 is not bigger than 2, 1 is not bigger than 3, 1 is not bigger than 3, and 2 is not bigger than 3. But when it comes to 1, 3, 2, we do have 3 before 2. It does have one inversion. 2, 1, 3, you have 2 before 1, and 2 is bigger. 2 is before 3, but 2 is not bigger. And 1 is before 3, and 1 is not bigger. So there's just that one inversion. 2, 3, 1. The only inversion is 3 is before 1. Excuse me. 2 is also before 1. And 2 is bigger. So it has 2 inversions. 3, 1, 2. It has 1, 2 inversions. 1 is not bigger than 2. 3, 2, 1. 3 is bigger than 2. 3 is bigger than 1. There's 2 inversions so far. And 2 is bigger than 1 as well. It has 3 inversions. Okay. So now what I do is I put these permutations down. 1, 2, 3. 1, 2, 3. And since there's an even number, a plus goes in front. Then 1, 3, 2. 1, 3, 2. That has 1 inversion. That's an odd number. Put a minus there. And then we have 2, 1, 3. 2, 1, 3. It has 1 inversion, odd, so a minus goes in front. Then we have 2, 3, 1. 2, 3, 1. It's 2 inversions, even, plus goes in front. Then we have 3, 1, 2. 3, 1, 2. 2 inversions. Put a plus in front. And then we have 3, 2, 1. Odd number inversions. 3 is odd. 3, 2, 1. This here is the definition of the determinant of a 3 by 3. So for example, if you're given numbers 7, 2, 1, 0, 1, 4, 3, 1, 2, and you have to use the definition. Well, first you write down A11, which is 7, and then you write down A22, which is 1, and then A33, which is 2, minus, and then you write down A11, which is still 7, A23, which is the 4, A32, third row, second column is 1, etc. But nonetheless, you have to have this definition. Okay, I wrote down an arbitrary 3 by 3 determinant, and I used the definition to calculate the determinant. Now, if you're ever asked to do this, say with the matrix that I'm about to erase, you have to do what I have in the green in the middle. You have to use the definition. You have to derive the definition. And all it is you, for 6 terms, you write down all the permutations. The permutations are what I wrote in green. The first permutation is 1, 2, 3. The second one was 1, 3, 2. The last one was 3, 1, 2. Okay? So there's a definition, and you absolutely can go and memorize this definition, and you will have a method of calculating the determinant of a 3 by 3 matrix. But of course, that's somewhat hard to do. That's somewhat hard to do. So let's try to figure out another way. And we won't figure it out. We'll use what other people have figured out for us. And sometimes I'm thoroughly impressed at how people recognize patterns. If you want this determinant, what you can do is you can write the matrix down again. Write the matrix down again, which isn't hard. And then repeat the first column, A11, A21, A31, and then repeat the second column. A12, A22, A32. I'm going to have to start writing up here. If you multiply those three entries, A11, A12, A13 plus, and then you multiply the next three entries, A12, A23, A31 plus. Actually, let's put the plus in front. Plus, now you multiply those three, A13, A21, A32, close the bracket, and then you take away the next product. It goes, the next term, it goes this way. A31, A22, A13 plus this product. A32, A23, so let me write that. A23, A11 plus that product. A33, A21, A12. Close that up. That will give you exactly what I have using the definition. For example, this term right here, A11, A12, A13. I'll find it somewhere. Okay, I don't know what I'm thinking, but let's be honest. When I multiply those three, I didn't get what I said I got. I got A11, A22, A33. Not sure what happened there. But that's this term. And I also then I got A12, A23, A31 plus. I got this term, including the plus. Okay, then I have A13, A21, A32. Exactly this one, with the plus in front. Now, I start taking away the sums. So those are gone. The next one is A31, A22, A13. It's this one. Now you may say, well, no, it isn't. The A31 came first. Well, these are real numbers. A13 is the entry in row 1, row 3 position. These three numbers, I can interchange any two. Well, that gives me exactly A31, A22, A13. Okay, and then the next one is A32, A21, A12. Okay, this one up here with the minus in front. Remember, I'm taking away that term. And then I'm going to take away A33, A21, A12, which is this term. If you notice, everything that I have circled in that big green box, whatever you want to call it, everything in the big green has been circled in black. That is, they really are equal. This tic-tac-toe method works. This tic-tac-toe method actually works. Also known as the spaghetti method. So let's look at this on a more mechanical viewpoint, and let's see how you calculate the determinant of a 3 by 3 matrix using this spaghetti method. 7, 1, 4, 2, 1, 5, 3, 0, 1. The first thing you do is copy it down. 7, 1, 4, 215,301. And the first column, 723, write it down at the end, and then write down the second column at the end. And it's going to be one set of numbers being added minus another set of numbers. You multiply these numbers. 7 times 1 times 1 is 7, plus 1 times 5 times 3 is 15, plus 4 times 2 times 0 is 0. Please, if you multiply a string of numbers and one of the digits is 0, please get a 0. Multiply these three numbers, you get a 12, plus these three numbers, one of them is 0, so you get a 0, plus these three numbers is 2, so you get 22 minus 14 minus some silly error I made. The answer is 8. Spaghetti method. It works fine. But I need to feel good about myself, and I just can't give you these rules. You have to see that it works. And we use the definition, and then we verify that this strange technique, crossing out three numbers at a time, adding them, subtracting them, actually gives you the right answer. It doesn't work because I told you it works. It doesn't work because your teacher told you it works. It works because we use the definition. We got our answer, and we notice that when we use this spaghetti method, it also gives us the same answer. That's why it works. Negative 2, 1, 4, 0, 1, negative 3, 1, 1, negative 1, and then 3. That's 3. So suppose you want to find this determinant. This is rather mechanical. Write down the matrix that you want the determinant of, and then these two get added at the end. Those two columns go at the end. Multiply those numbers, you get what you get, plus you multiply those three numbers, you get what you get, plus you multiply those three numbers, you get what you get. Minus. Now you go the other way. You multiply these three numbers, you get 4. Plus those three numbers, you get negative 6. Those three numbers multiply out to 0. Now it's arithmetic. You have to know how to add and subtract sign numbers. First bracket is negative 9. The next bracket is negative 2. And that gives you negative 7. Okay. Multiplying numbers, that's not part of a linear algebra course. You need to know how to multiply numbers and to add and subtract sign numbers. So what you to take with this video is to know which columns to multiply, and then which column and add together, and then which columns to multiply, add together, and take away. So if you didn't see it, just go back and watch the video again and again until you get it. The numbers really have no play in this. Hey, just because I give you the right 9 numbers in a 3 by 3 matrix, the light bulb is not going to suddenly go on. There are no right numbers. There are some wrong numbers, like if all the digits are 0, all the entries are 0, maybe that wasn't the brightest one. But what you need to just understand is that you have 9 numbers for 3 by 3. So you want to find the determinant of this. You write down those 9 numbers, which I'm not doing, as you can see. And then this column goes here. And the next column goes here. And then you're going to multiply these 3 numbers, and you're going to get a number. Plus, you'll multiply those 3, and you're going to get another number. You're going to multiply these three, and you're going to add on that product. Minus. You're going to multiply those three and get a number. Plus. You're going to multiply those three, get a number. Plus. You're going to multiply those three and get a number. If you can say that, you have it. Okay, so long as you know how to multiply numbers. You need to just know the pattern. Don't just do problem after problem. Memorize the steps. Now, when it comes to the spaghetti method, there's nothing to really understand. It's just, it just happens to work. Absolutely, it just happens to work. You can't understand, oh yeah, it works. And if you say, yes, you can, well, yeah, it was the argument I gave you using the definition. I calculated the definition. I know the exact answer for the determinant of a general 3 by 3. And then I happen to notice that the spaghetti method is equivalent. It gives the equivalent result. How about that? Okay. On to our theorem. The determinant, so let's call it a theorem. The determinant of A and the determinant of A transpose, they're equal. Okay, the determinant of A and the determinant of A transpose, they're equal. Let's look at a couple of examples. If you have 3, 1, 2, 1 or 3, 1, 2, 4, that's a matrix, and the determinant will be 12 minus 2 times 1 is 2. You get 10. Now the transpose. The first row is 3, 1. All right, 3, 1 is the first column. The second row is 2, 4. Well, that's going to be my second column. 4 times 3, or 3 times 4 is 12. 1 minus 1 times 2 is 2. Look at that. I got the same answer. Now, if I have a 3 by 3, 1, 4, 1, 0, 0, 1, 1, 2, 1. Well, the transpose will be, instead of 1, 4, 1 as the first column, becomes the first row. Instead of 0, 0, 1 as the second row, it becomes the second column. And the third row, 1, 2, 1, just becomes the third column. Well, we'll calculate this first determinant, like all 3 by 3s, for now at least. You write them down and you repeat the first column and then the second column. This product is 0. This product is 4. And the next product is 0. Minus. This product is 0. The next product, 2 times 1 times 1 is 2. And that last product is 0. The first bracket is 4. Minus the second bracket is 2. 0 plus 2 plus 0 is 2. 4 minus 2 is my answer. That is, it equals 2. Well, let's try what the transpose matrix. 1, 0, 1, 4, 0, 2, 1, 1, 1. You repeat the first column. You repeat the second column. This product is 0, because one of the factors were 0. That product is 0. This product is 4. Minus. This product is 0. 1 times 2 times 1 is 2. And that product is also 0. So you just have 2. 4 minus 2 is 2. And yeah, they are equal. They really, really are equal. Now, I gave a couple of examples that show that this theorem above, I verified that theorem using those two examples. But this theorem says a lot. Well, I was very glad my teacher clearly stated what major thing this theorem says. Now, let's just suppose this theorem is true. It is not true. It is not true. But let's suppose it. Suppose if A has a row with all even entries, then the determinant of A is 72. That is, I mean, this is absurd. It's not true. But let's take it for being true right now. That is, if you have 3, 1, 4, 2, 8, negative 6, 1, 2, 3. That second row has all even entries, so the determinant is 72. But now, let's look at this matrix. 2, 4, 1, 3, 0, 2, and, I don't know, 7, 6, 1. Let's look at this determinant. That column has all even numbers. 0 is even. But you know what? That determinant is equal to the transpose determinant. And look at this. Column 2 had evens, and now when I switch it around, row 2 has evens, which means, oops, I didn't mean to put the bracket, the bar, which means the determinant is 72. What I'm trying to say is that theorem on the very top, any determinant theorem that talks about rows, you can also say is true for columns. If A has a row with all even entries, then the determinant of A is always 72. Well, if A has a column with all even entries, then the determinant of A will be 72. Why? Because the determinant of A transpose is 72. Because when you take, if a matrix has just a column of zeros, I take that back. If a matrix has a column with even entries, then the transpose will have a row with all zeros. And the determinant of A transpose will be 72. But according to this theorem above, the determinant of A equals to the determinant of A transpose. So even if you have a column that has all even integers, whatever true statement, and this is not true, whatever true statement you can tell me about rows of our matrix with respect to determinants now, you can say the same thing about columns. You can even reverse that. If there's a theorem about columns and determinants, you can cross off columns and put rows instead. They have this togetherness. Whatever determinant theorem is true about rows must be true about columns. Whatever determinant theorem is you have that's true about columns, then it has to be true about rows. If it weren't for this theorem at the very top, you would actually have to prove those theorems twice. Once for rows, one for column. But that theorem that remains on the board, it tells us, you only have to do it once. You only have to do it once. You don't have to prove it for rows and columns. It's enough to prove it for one, and then it's true for the other. I hope that was clear, and that should make your life a little bit easier. Okay. Now, I want to prove something. And I'm not going to really rigorously prove it. You can write it off. I'll do a good job in explaining it. Suppose you have Okay, so here's the claim. If you interchange two entries in I don't like the way I'm wording it. Sorry. Claim. You have a permutation on the set 1 through n. If you interchange any two entries in this permutation, then the parity changes for the number of inversions. Parity is odd or even. So the odd even changes for the number of inversions. That is, if you have a permutation 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the permutation on 1 through 10. N is 10. If you, and this, our permutation has a number of inversions, which means it's odd or, the number of inversions will be odd or even. If you were to switch the 9 into 6, the parity will change. For example, if this is even right now, if you interchange the 9 into 6, it will become odd. If it's odd right now, and then you go and you interchange your 9 into 6, it will become even. The parity changes. Now, why is that? Okay, well, let's suppose we really wanted to interchange the 9 into 6. Now, here's how we will do it. Okay. First, I need to convince you that if we interchange two that are right next to one another, the parity won't change. Let's look at this one. You have that one, and I'm going to switch a 10 into 1. Coincidentally, they're our highest and lowest number, but that's honestly coincidental. Okay. Now, 5 is the first one. Now, either 5 is less than 10 or more than 10. And 5 is less than 1. 5 is before 10 and 1. 5 is before 10 and 1. Well, so it is over here. It's before 10 and 1. The parity with respect to... Okay, so the parity won't change just because I interchange 5 and 10. I mean, 5 is still before 7. 5 is still before 9. 5 is still before 2. 5 is before 10 like it is here. 5 is before 1 like it is here. 5 is before 8 and 6 and 3. And 5 is before all of these numbers. You know what? 7 is before all of these numbers. 9, 2, 10, 1, 8, 6, 3, 4. You know what? That 7 is still in front of the same set of numbers. that 7 is still in front of the same set of numbers. Since I wrote on it so much, let me write down some more. Let me write it down again. Now, same argument with the 9. In both cases, the 9 is still in front of the 2, the 10, the 1, the 8, the 6, the 3, and the 4. In both cases, one to the left and one to the right, the 9 is still in front of the same set of numbers. The 9 is in front of these numbers. It's even over here. The 9 is before those numbers. Let's not worry about the 2 versus the 10. But you know what? The 2 and the 10 are before those numbers. Even over here, the 2 and the 10 are before the same exact 5 numbers. 1, 8, 6, 3, 4. And of course, these numbers being exactly the same, the 1 is before 8, 6, 3, 4. The 1 is still before 8, 6, 3, 4. Nothing's changing there. Oops. I meant to write this in the reverse order. 10, 2. The only thing that changed is here we don't have an inversion with the 2 before the 10 because 2 is not bigger than 10. Here we do have an inversion. We had one more inversion. If we went from this one to that one, here we had an inversion and now we don't. So the number of inversions went down 1. If this had 11 inversions for these, well, it can't have 11. There's only 10 numbers. But that's a whole nother story. If this whole thing had 7 inversions, then this over here will only have 6 because we no longer have the inversion from 2 to 10. The number of inversions either goes up 1 or goes down 1. But like 7 is odd. If you go down 1 or you go up 1, it becomes even. If it originally was even, and then you change 2 consecutive ones, either the inversions will go down 1 or up 1. Odd. Odd becomes even. Even becomes odd. The parity change. If you interchange 2 right next to one another, the parity will change. Okay, let me write down the numbers. And then we'll interchange 2 that are not right next to one another. I want to have the same ordering, so let me write it down before I erase it and forget it. 5, 7, 9, oops. The original one had the 2 first. 2, 10, 1, 8, 6, 3, 4. Okay, let's suppose we want to change the 6 into 2. We want to change the 6 into 2. Now, or let's say I want to get the 6 next to the 2. The 6 is right here. I can move it one place to the left by interchanging the 8 and the 6, and then the 6 and the 1, and then the 10 and the 2. Okay? Now, so the 6 is right here now. I moved it 1, 2, 3 places. Now, if I wanted to move the 6 back, I would go 1, 2, 3 places. That is, moving the 6 from here to there, and then moving it back is going to be the same number of moves going to the left and the same number of moves going to the right. Well, that's an even number. If you go 5 to the left and then 5 back to the right, you win an even number. But you may say, but what is he talking about? He didn't switch the 6 into 2. Absolutely right. You have 5, 7, 9, 2, 10, 1, 8, 6, 3, 4. You move this 1, 2, 3 places. So now, 3. So now let's put it there. You have 2, 6, 10, 1, 8, 3, 4. Okay. My goal is to switch the 2 and the 10. Sorry, the 2 and the 6. Now I do one move. I actually switch the 2 and the 6. Now, instead of moving the 6 back, I move the 2 back. It's going to be the same number of places it took to bring the 6 to the left of the 10. And take 1, 2, 3 places. No matter what that first number is, it's going to be the same as the last number. You add 2 of the same numbers, you always get even. But then you add one more, which is odd. You're going to have an odd number of permutations. You're going to have an odd number, inversions. You're going to have, no, I take that back. You're going to move 2 consecutive ones an odd number of times. Each time you move it, it changes parities. Every time you move it twice, 7 is 2 plus 2 plus 2 plus 1. If you're odd, and then you go even back to odd, you're now odd. So you're odd, you go to even, go back to odd. It changed twice. You're odd now. You're odd. You change 2 times. You go to even, that's one change, back to odd. You started with odd, you're back at odd. But then you go one more, from odd to even. If you interchange 2 at a time, an odd number of times, you're going to have the parity is going to change. You're going to change the number of inversions by an odd amount. Okay, you're going to change the number of inversions by an odd amount. I think it's important that you understood what I just said. If you didn't, all you have to do is count the number of times that you have to interchange 2 consecutive ones. So in the end, you move 2 that are not consecutive. 1, 2, 3, 4, 5, 6, 7, 8. Suppose you want to move the 8 into 6. First, move those 2. So 5, 2, 4, 7, 1, 6, 8. And then move these 2. 5, 2, 4, 7, 6, 1, 8. And then move these 2. 5, 2, 4, 6, 7, 1, 8. And that took a certain number of moves. Okay, it took 1, 2, 3 moves. And then the next move, which I really don't want to count, but I'm going to put it, so now I have 5, 2, 6, 4, 7, 1, 8. And now I want to move the 4 back. Well, there's obviously, okay, there should be a 3 on all the ends. Sorry about that. Now I want to move the 4 back. Well, I want to move 4 to where the 6 were. Well, if it took me 3 moves to get this 6, right before 7, 1, 8, 3, well, now I have 4 instead before it. It's just a number. In other words, the number of times it'll take for me to get the 4 over there is not dependent upon the fact that it's a 4. You can't say, well, let's see, 1, 2, 3 times. But if this was an 11, it wouldn't be 3 times. Of course it would be. So this is like 1. We're going to think of this as a group as 3. And then I'm going to move the 4 back. So why do I have a 4? Okay, and now I move the 4 back. That is, I switch the 4 into 7. 7, 4, 1, 8, 3. I'm going to call that 1. The 4 going back, that's the first one. Then I interchange the 4 into 1. 5, 2, 6, 7, 1, 4, 8, 3. That's the second move for the 4 going back. And then I switch the 4 into 8. And I get 5, 2, 6, 7, 1, 8, 4, 3. So in the end, I switch the 8 into 4. Bringing the 6 to where the 4 was took as many moves as moving the 4 to where the 6 used to be. But then there was that one extra move, moving the 4 and the 6, interchanging the 4 and the 6. It's going to be an odd number of moves. And every time you going to be an odd number of moving 2 next to one another. I think they call that a transpose. Transposing. Something like that. But the bottom line is, if you want to interchange any 2, it's going to take an odd number of moves. A move is interchanging 2 that are consecutive next to one another. And every time you move 2 that are next to one another, the parity goes up or down 1. Sorry, the number of inversions goes up or down 1. That is, the parity changes. And if you do 2 of these, the parity changes back. Sorry, the parity changes 2, and you're back to where you were initially. If you change the parity an odd number of times, that's equivalent to just changing it 1 time. Okay. So what we learned here in this theorem is that if you interchange any 2 numbers in a permutation from on the set 1 to n, it will be, the parity will change. That is, the number of inversions will change parity. Okay, so now we want to talk about a theorem. I'm going to talk about this pretty cool theorem. And this theorem says that if one matrix is obtained from another by interchanging 2 rows or 2 columns, think about that, then their determinants, one equals the other with a sign change. Okay, so let's state this formally, more formally, and we'll be done. Theorem. Let B, which I'll denote by Bij, little Bij, be obtained for matrix A, which I'll call Aij, by interchanging 2 rows of A. So if A is equal to 1, 1, 1, 2, 0, 1, 3, 1, 2, then B could be 1, 1, 1, 3, 1, 2, 2, 0, 1. I interchanged row 2 and 3 to get matrix B. Then, it's not a big deal, but let me write if B is obtained the way that we just said, then the determinant of B and the determinant of A are not equal, but they differ by a sign. They differ by a sign. And that is what we want to prove. Okay. Now, before doing that, I probably should have used the example that I just erased, but before proving it, let us actually see that it's true for a matrix and another matrix that was obtained by interchanging 2 rows of the original matrix. I'll write down matrix A. Matrix A is 1, 0, 1, 1, 1, 1, 2, 0, 1. And matrix B is going to be, I'll interchange the first 2 rows. And I want to show that the determinants differ by a sign. 3 by 3, spaghetti. That is, repeat the first 2 columns. At the end, you get 1 plus 0 plus 0 is 1 minus 2 plus 0 plus 0 is 2. 1 minus 2 is negative 1. This determinant will be solved by tic-tac-toe or spaghetti on this. That product is 0. That product is 0. That product is 2. Add those numbers up. You get 2 minus 0 plus 0 plus 1. 2 minus 1 is 1. Yeah, look at that. Look at that. They differ by a sign. That's what this says. It says the determinant of A and the determinant B differ by a sign. This is equal to negative the determinant of B. Why is that? Because negative is negative and determinant of B is 1. That is what it says. So yeah, the determinant of A does equal to negative the determinant of B in that example. I wrote down matrix A. I found this determinant. For matrix B, I just interchanged 2 rows of A, and then I took the determinant of that matrix. And I noticed that the 2 results differ by signs. And I said, yeah, it's true. Okay, but we want to prove this beyond the shadow of a doubt. Proof. Let B be obtained from A by interchanging row R and row S of A. Okay, so we interchange row R and row S. Now, all the other rows, matrix A and matrix B, have the same entry. Okay, so Aij and Bij are equal to one another if I is not R and I is not S. I is not R and I is different from S. If we're not talking about row R or row S, they're equal. But what if we are? What if we're talking about row R? BRJ. The rth row, some column position. Remember, this is row R and this is row S. And this is matrix A. Okay? Now, when it comes to matrix V, when it comes in, I don't know how to write it, but here, I'll write it. This is row S of A. Remember, they get B. I switched these. This here is row S of A. Sorry, row R of A. Because row R is now in row S's position. So, this is row R. This is row R. Make it really clear, and that's row S. But these entries are the entries from row S of A. The columns didn't change. If this is the J's column, well, fine, it's the J's column. So BRJ, which is right there, that's an entry in of matrix A in column J. It didn't change column, but is now row S. This entry went there to get to matrix B. This is row S. And when it comes to the BSJ entry, this entry right here, it came from here, of A. It came from here. It came from row R, J's column. Row R, J's column. Okay? So it really is what I say it is. It isn't because he said it, so he must be right, or he doesn't know what he's talking about. I don't agree with that. Okay, you have to either be able to convince yourself on a rigorous level that I made a mistake or that I'm right. Either way, you have to be able to understand why I'm right or wrong. You just can't say, yeah, that's right, or no, that's not right. You have to say why. Okay. So now, what is the determinant of B? The determinant of B, by definition, is the summation plus minus B1, J1 times B2, J2, all the way up to, well, let me say one other thing. Assume R is less than yes. After all, one row the rows can't be the same. So one row has to be before the other. Okay, then we have BR, JR, and then later on BS, row S, JR column, JS column, excuse me. And then you have the nth row, JN column. Now, most of the time, I can just replace the B's with an A. This is the summation of A plus A1, J1, A2, J2. But this one, that's AS, JR. The column didn't change. And this here is AR, JS. All the way up to AN, JN. Okay. Now, this here are real numbers. Well, these are real numbers. These are real numbers. And now they're out of order. I mean, suppose there were 10 rows. Row 1, row 2, row 3, 4, 5, 6, 7, 8. I lied. There's only 8 rows. And I interchange 3 and 5. Well, then they're not in order. Maybe that's 3 and, well, this is 5 and this is 3. Well, I don't like that, but they're real numbers. So I can switch the order. This is A1, J1, A2, J2, all the way up to AR, JS, all the way up to ASJR, all the way up to ANJN. That is, I just switched these. But, you know, is that equal sign 100% right? Yeah, they're real numbers. I agree. I will agree that this 100% equals that. But there's more. There's the sign. Is it plus or minus? Well, what I did was, let me just erase something from the top. What I did is I switched two entries in the permutation. Say we have 8 again. Maybe the permutation was, well, let me finish writing. 1, 2, 3, 4, 5, 6, 7, 8. Maybe that's the permutation. And I'm switching 3 and 6. In other words, that's J1, that's J2, that's J7, and that's J4. Well, actually, it doesn't matter. I mean, here, it doesn't matter if I call this 3 or not. 4, J5, J6, J7, and J8. Now, if I switch the 6 and the 3, well, then I have J1, J2, J7, J4, J5, J6, J3, J8. That is, I switched two numbers. I no longer have 2, 5, 6, 1, 4, 7, 3, 8. The 3 is here and the 6 is there. And we know one thing. When you switch any two numbers in a permutation, the parity changes. That is, I have to factor out a minus sign. Now, here is that minus sign. But by definition, that there is a determinant of A. So the determinant of B really does equal to negative the determinant of A. To get these last two lines equal to one another, I had to pull out a minus sign. Now, how I number these, I don't have to call this J1 and this J2 and that J17 and that J20. I don't have to call it that. I can if I want. The bottom line is we had a permutation and we switched two of them. Two entries in that permutation that changed the parity. Okay, now go and think about all of this for an hour or two. You need to settle it in your head completely. I once had a professor when I was an undergrad student say that it wasn't good that I would think about things until I completely settled it in my mind. Now, his comment was not, you know, Steve, it takes you too long to settle things. That would have made me feel really bad. That means one is not smart if it takes too long to figure out things, or not very smart. But what he said was, it's not good that you do that, and he was completely wrong. You don't accept anything until you completely believe it. Rock solid. It's like 1 + 1 = 2. If it isn't 1 + 1 = 2, you have to go back and revisit it. You have to understand it perfectly. Okay. Now, so now I remembered And every once in a while, it wasn't too often, but every once in a while, my teacher would put a proof up on the board, and I would see, we took like once or twice for my undergraduate degree and 0 times for my graduate studies. This happened. But every once in a while, every 5th year or so, I saw what the next theorem was going to be. And this was one of them. If you interchange 2 rows of a matrix, those 2 matrices, one where you didn't interchange the 2 rows and one where you did interchange the 2 rows, they differ by a sign. And I immediately thought, what if the 2 rows that you interchange were the same? What if matrix A was this matrix? What if this is matrix A, and I obtain matrix B by interchanging row 1 and 3? Now, nowhere in this theorem did it say any exceptions. Oh, the determinants differ by a sign unless you interchange rows that only had even numbers with rows that had odd numbers. It didn't say anything like that. It didn't say anything like that. To get B, I interchange row 1 and 3. Well, I know that whatever the determinant of A is, it has to be, determinant of B has to be negative the determinant of A. But you know what? B and A are equal. Just look at them on the bottom left. B and A are equal to one another. B is equal to A. Hence, their determinants are equal. So I have B, determinant of B is equal to negative determinant of A, and the determinant of B equals A, the determinant of A. So these two, since they both equal, the determinant of B must be equal to one another. And there's only one way out, and that's if the determinant of A is 0. Negative 0 is equal to 0. But negative 5 doesn't equal 5. If A has 2 identical rows, now again, we're only talking about square matrices. So I can't give you a 4 by 3 matrix. 1, 2, 3. 1, 2, 3. 1, 1, 1. 0, 1, 1. And you tell me, oh, the determinant of this is 0. No. It has to be a square matrix. If A has 2 identical rows, then the determinant of A is 0. The proof, I kind of sketched it very nicely on the bottom. Let A have identical, I'm just not saying it right. In matrix A, row R and S are equal, are the same. Row R and row S are identical rows in A. Let B be obtained from A by interchanging row R and S. Let B be obtained from A by interchanging row R and row S. Okay. From the previous theorem, we have that the determinant of B is equal to the determinant is equal to negative the determinant of A. But B and A are equal. And to change the same two columns, you don't get anything different. So matrix B and matrix A are equal. And they're square matrices, so that implies that they have the same determinant. It's not reasonable, forget about B for a moment, it's not reasonable that the determinant of that matrix and the determinant of that matrix are different. They're the same matrices. You can call them A, B, or C if you choose. But they're the same matrices, so the determinants are equal. But this statement and this statement implies this statement. B equals that, and B equals that. Well, let me say it differently. B equals this, and B equals that. So this must equal that. If everything and anything that equals the determinant of B are equal to one another. But now remember, the determinant of A is a real number. Call it X if it makes you happier. X is equal to negative the determinant of A, which is X. I mean, if I let X be 7, so I have 7 and then equals and then a little dash and then 7. 7 equals negative 7? No. Only 0 equals negative 0. Because negative 0 is 0. So that implies the determinant of A is good old 0. You interchange two rows, if a matrix, excuse me big times, if a matrix has two identical rows, a square matrix of course, then the determinant of that matrix will be 0. And there's a million things to remember at the same time in linear algebra. That was the hardest thing for me for this course. Anything my teacher said, I understood pretty much completely. But it was just to remember. You know, if you're talking about matrices, determinants, you can only talk about square matrices. You have to know what upper triangular means, what a skew matrix means, what a scalar matrix means, what a diagonal matrix means. You have to know you can only take inverses of square matrices. You have to know identities. You have to know a lot of things. Okay, so suppose you have 1, 0, 3, 0, 1, 0, 1, 0, 3. Clearly as can be, the first and third rows are equal. So you just repeat this. And I do want to make one change in the theorem at the very top. Remember, I could say columns as well as rows. This is 3 plus 0 is just 3 minus 3 plus 0 plus 0. Oh, 3 minus 3 is 0. And if I played the same game with columns, so two rows were the same, and we got the determinant to be 0. It's going to be the same exact situation when we talk about columns being the same. Try it out with their 2 by 2. Convince yourself. 3, 1, 4, 1, 2, 2, 3, and I'll change that to 1, 2, 3. So the last two columns, they're equal. So what's the determinant? Well, unless we make a mistake, we're going to get 0. 3, 1, 2, 1, 2, 3. This is 18 plus 4 plus 3. 25 minus 2, 18, that's 20, and then 3. So somehow I'm not getting what I should be getting. Column 1 and 2 are clearly the same. Column 1 and 2 are column 2 and 3 are clearly the same. I want to make sure I wrote down the matrix right. And then this product is 18 and 4 and 3. And this product is 4. Okay, not 2. So I just added 2. That's going to make this 25. 25 minus 25 is 0. Okay, it works. It works all the time. If a square matrix has 2 identical rows, the determinant is 0. We proved it. There's no leeway here. It's valid. You can't say it's not true. You'd be wrong if you attempted that. Going to look at this theorem now. What if a row or column of a matrix A consists of all zeros? What should the determinant be? If a row or column of the square matrix A has a row that, I already said row. Okay, if a row of A has only zeros, in it, then the determinant of A is 0. And this is kind of obvious because remember, the determinant of A, well, let me just start the proof a little bit. Suppose, I want to label the row. Suppose row R of A, or column R of A, consists of only zeros. Okay. Now, the determinant of A, by definition, is the summation plus minus of A1, J1, row 1, some column, times row 2 times some column. That is the row 2 some column entry. Row 3 some column entry. All the way up to row R some column entry. All the way up to row N some column. Now remember, if this is column 1, that cannot be column 1 because J1, J2, J3 up to Jn, the J1 through Jn is a permutation of the n, the first n counting numbers. You know what I mean? If n was 8, one permutation might be 1, 3, 5, 6, 8, 2, 4, 7. I used 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. You have to use all of that. Okay, and what we're going to do is, forget the plus minus in the front for a moment. We are going to add up many of these. And what is the difference between the things that we're adding up? The columns that we pick are going to be different. They're going to be permutations of 1 through 8. But the bottom line is, we are, in each term that we add up, and this is the terms, what the terms look like. Each term is going to have an entry from row R. Each term is going to have an entry from row R. And as you add up, what's going to change is the column. First you'll have, at some point, maybe first you'll have row R, the third entry, and then for this first term. And of course, it's going to be 0. And if you multiply all of these numbers, and this one is 0, then the whole product is 0. And then plus, then you're going to come to, this is going to be AR, the fifth column. And it's going to be 0. Because no matter where you are, no matter which column you're in row R, it's 0. Matrix A, I guarantee you, in row R, they're all zeros. Doesn't matter whether you're in column 3 or column N or column 1 or column 2, you keep getting zeros. And every term in the definition has a factor from row R, AR, JR. So that whole term, that whole product is going to be 0. You're going to keep adding up zeros, and when you add up zeros, you get 0. In fact, you write up the proof now. I gave a good argument. In fact, I said everything. Just put the pieces together. Again, every term in the definition, and here's the proof. Just write it down. Every term in the definition contains a factor from row R. But every entry in row R is 0. So each term will have a 0 factor. Factors, remember, factors are things that you multiply together. A1, J1 times A2, J2. All of these AI, JIs are factors. And if one of them is 0, the whole product is 0. So again, the proof goes as follows. Suppose row R of A consists only of zeros. I'll write it off. In the definition of the determinant of A, each term, those are the things we're adding up, is that long mess A1, J1, A2, J2, etc., plus A1, and now we have a different permutation called a J1 prime. We have a different permutation on their columns up to AN, JN. That's the second term, plus the third term, plus the fourth term, up to the nth one. Each term has a factor from row R. This factor from row R is always 0. Hence, each term in the definition of the determinant of A is 0. Therefore, the determinant of A is 0 itself. You keep adding up zeros, you get zeros. That's all that theorem is saying. If matrix A has a column of zeros, and it's the square matrix, you don't have to go too far to figure out what the determinant is. The determinant of that square matrix will be the round number 0. Maybe a square matrix, but the determinant is 0. look at a couple of examples. 2, 3, 0, 0. Well, of course this will be 0, because 2 times 0 is 0, minus 3 times 0 is 0. Each thing that I added up, picked, every time I look at a product, whether it's 2 times 0, it took an entry from from row 2, and when I did 3 times 0, it took an entry from the second row. And those entries are always 0. You have 1, 3, 2, 1, 4, 5. So I want to write the zeros in a different color. The zeros of that row. And we can even have another 0. But since it's not in the row that has all zeros, I'll keep it that color. To write this down, you write down the first row, the third row, and then the second row. And you repeat the first column, and in row 2, it's 0, and you repeat the second column, and in row 2, it's 0. I did write down I will write down 1, 0, 1, which is column 1. And I will write down 3, 0, 4. And this is going to be, now, watch what I'm saying. When you multiply the first diagonal, you get that 0 as a factor. So the product is 0. Plus, when you multiply the second diagonal, you pick up something in row 2, namely that 0. So the product is 0. In the third diagonal, you pick up something from row 2, which is always 0. I mean, just look at row 2. So you're adding zeros. Minus, in this computation, in that product, oh, look, something from row 2. And the next one, 4 times 0 times 1. You picked up something from row 2, which is a 0. In the last diagonal, fine, you picked up a 0 here. Fine, so the product is 0. But you know what? We also picked up something from row 2, which is 0. It's going to be 0. Every time we look at A1 something, so let me write it down. A1 something times A2 something times A3 something. After all, the determinant of A is adding up things that look like that, where you put things in for the column. But you know what? This is going to be 0. Because whether you're in column 1 or column 2 or column 3, A21 is 0, A22 is 0, A23 is 0. And when you add up all things that look like that, you just get 0 plus 0 plus 0. 0. You're always going to be taking something in each term, and these are the terms. One of the factors will always be from row 2. A2 something. No matter what that something is, and it's a row number, it's 0. A21 is 0. A22 is 0. The A23 entry is also 0. Everything in row 2, regardless of the column, is 0. The only time that isn't true if you talk about A24, and there is no fourth column. But the definition doesn't do that. Definition stops at column 3. If it's a 3 by 3 matrix. Okay, I hope that's clear. Well, what if you multiply a matrix, a row of a matrix, by some constant? What if you multiply, to get matrix B, you take some row of A and you multiply it by C? what can you tell me about the determinants of A and B? Are they equal? Okay. If B, which I'll denote by Bij, is obtained from A, is obtained from matrix A, which I'll denote as Aij. So if B is obtained from A, by multiplying some row of A by C, then the determinant of B and the determinant of A are not equal, but C times the determinant of A will give you B. Okay. So proof. So now you declare or state what precise thing you're doing to get B from A. Suppose B is obtained from A by multiplying row R of A by the number C. So, as long as you stay away from row R, Bij and Aij are equal if the row is not R. But what if you are on row R? Well then, if you take Arj and you multiply it by C, this is just some entry in row R. It's the jth entry. It's an entry in row R, but column J. Well then, you're going to get Brj. If you multiply each entry in row R by C, you get the B entry. You get the entry, the rth row of B. Okay. So, we go to the definition. The definition of the determinant of B is the summation of plus minus, B1, J1 B1, J1, B2, J2, all the way up to, say, BR, J sub R, all the way up to BN, JN. For most of these B's, I can replace with A. B1, J1, well, that's row 1. It's not row R. I know it isn't, because row R is here. So I get A1, J1. B2, J2 is A2, J2. The only one that changes is this one. It becomes C times Arj, all the way up to Bn, Jn. Now, everything's being multiplied here. The A1, J1 changes as we sum up. That is, first maybe J1 is 7. So it's A1, 7, and maybe J2 is 3. But the next time around, they change, because we're doing a permutation. In fact, they may not change. I mean, if you look at a permutation on 1, 2, 3, 4, that's 1. And here's another 1. And notice that, if I call these J1 and J2, Notice J1 and J2 did not change, but they can. They can. But you know where can change is that C. I can pull that C out in front of the sigma. And then I have plus minus A1, J1, A2, J2, all the way up to AN, JN. Well, the C is in front. This, by definition, you see something that looks like that, you say, oh, that's the determinant of A. So the determinant of B is really, really C times the determinant of A. If you multiply one row by some number, the determinant of this new matrix will be that number times the determinant of the original matrix. So why don't we look at that? Remember, whether you do it to rows or columns, the theorem follows. So let this be A. A is 1, 2, 3, 4. And B, I'm going to get by multiplying column C by 2. So B is, first column stays the same, but the second column gets double. Okay. Now, what is the determinant of A? And the answer is it's 1 times 4 minus 3 times 2. It's negative 2. And what is the determinant of B? Well, it's 1 times 8, 2 times larger than 1 times 4, and minus 3 times 2 is 6, because 3 times 4 is twice as much. And you notice that the determinant of B is twice that number. It's 2 times the determinant of A. Remember, the determinant of B is negative 4, and it does equal, unless it does equal 2 times the determinant of A, which is negative 2. 2 times negative 2 is negative 4. So it really worked. It really worked. Okay. It works for columns or rows. If you multiply any column or row by some number, including 0, the determinant of this new matrix will be that number times the original determinant, will equal to that number times the determinant of the original matrix. Original matrix is the one you did not change. If A is equal to 1, 1, 0, 0, 1, 0, 1, 1, 0. Oops. That's not a good one. 1, 1, 1. If I put that 0 in, the determinant will be 0. That's A. B, I'm going to triple the third row. So I get 1, 1, 0, 0, 1, 0. I triple it. Now, the question is determinant of B, is it 3 times the determinant of A? The answer is yes, yes. Let's verify. 1, 1, 0, 0, 1, 0, 1, 1, 1. Repeat, repeat. We get 1 plus 0 plus 0. Well, that's 1. Minus 0 plus 0 plus 0. Interesting. So it's just 1 minus 0 or 1. This one should be 3. 1, 1, 0. So the determinant of B is 0, 1, 0. Triple 3. Repeat the first 2 columns and see what you get. Now, if you think about it, every time in every product, Instead of multiplying by 1, we're multiplying by 3. Of course we're going to get 3 times as much. The first diagonal gave me 3, the second one is 0, and the third one is 0. And when we go the other way, it's still, instead of multiplying by 1, we're multiplying by 3. Coincidentally, one of the factors has always been 0. So we get 3 minus 0, which is 3. Okay, here. 3, determinant of b, does equal to 3 times 1. 1 being the determinant of a. Yes. If you multiply a row or a column by some number, that's how their determinant will be affected. If you have matrix A, whatever the determinant is, if you multiply each row by 11, this new matrix will have a determinant value of 11 times that original matrix. Whatever you multiply each row or column by, that's how it will affect the original determinant. The original determinant is 3. The original determinant of A is 3. And I'm telling you, I'm getting matrix B by multiplying every entry in some column by 14. The answer to the determinant of B will be 14 times 3. Okay, I multiplied some column of me to get matrix B. I multiply some column of A by 14. So whatever the determinant of A is, the determinant of B will be 14 times that number. Know that theorem. Know it well. Okay. If B is obtained from A by adding a multiple of one row to another row, then the determinants of A on B are equal. Now that one kind of surprised me, but if you think about it, it actually makes sense. Okay, proof. Suppose B is obtained from A by adding C times row R or column to row S. Instead of row, I can say column. Why? Because the determinant of A and the determinant of A transpose are the same. Suppose B is obtained from A by adding C times row R to row S. Okay. So, and B will be denoted as Bij and A, Aij. Okay. So now, a lot of times, Bij is just Aij. See? If this is A, and how about we assume R is less than S? Let this be row R, and lower down is row S. Okay, now when it comes to B, row R did not change. Row R, the same. I need a little bit more space to write this. Row R is row R. It's that row R. But now, row S is now different. Row S is C times row R plus row S. I have row S, and I added C times row R. So, from A to B, even row R did not change. The only thing that changed is row S of A and row S of B are different. So this is true if I, which is the row value, is not row R. It's not R. Okay? Well, what if it is row R? What will BRJ equal? Well, you get C times the row R entry in column J. That is, you get C RJ. Plus, you get the regular row S, which is, oh, now I do have a bit of a problem here. As I said very clearly, should listen to myself, is row R did not change from A to B, but row S did. I cannot be S. So what happens when we are in row S? Well, we get C times row R. In row S, we're talking about column J. We're going to get C times the RJ entry of A, the row R, J's column entry, plus we just get BSJ. Okay, now, of course, the reason I'm hesitating at this point is as follows. Everything I wrote, BSJ, CARJ, and BSJ, they are real numbers. And I have this real number is equal to something plus the same real number. Mathematically speaking, that must be 0. But that's not true. Okay, so I want to think how I can write that. And I'm trying not to think if I made this mistake in the past. All I can say is if I is R, okay. What I'll say is this. Even this bothers me. The I 8th entry, and I want to change that to R. Oh, of course what I'm... Okay, sorry folks. Sorry. Row S, I can write in terms of ARJ. So the BSJ entry will be C times R, C times ARJ, I took the j's column in row R entry and I multiplied it by C, and now I just add on ASJ. Okay, this did not have to be a B. All right, there it is. And of course, all of you saw that I was supposed to write that. Very good. So we go back to the definition and we work it out. We go back to the definition and we work out everything. What is the determinant of B equal to? The first thing you should do is write down the definition using BIJs. And then you convert those B's to A's. The determinant of B by definition is the summation plus minus B1J1, B2J2, and I'll stop off and say hello to row S, BS, JS. All the way down to BN, JN. Well, this is equal to the summation plus minus B1J1 is just A1J1. And B2J2, since we're not in row S, BIJs equal AIJ. That's I, 2 is I, and J is J2. A2J2. All the way up to BSJS. All I'm saying is it's not column J, but it's column JS. So you can put those S's in. It's C times ARJS plus ASJS. All the way down to BNJN. And I chose my words carefully. You could put those little S's in, but I don't want them. So I want to be able to say it in general. BSJ equals CARJ plus ASJ. Now, we have a sum. We can distribute. Let's distribute this. That is, we get the summation plus minus A1J1, A2J2 up to C, ARJS up to BNJN. I can use the same sigma, but I don't want to. Plus another sigma plus minus. Now I distribute this. That is, I get A1J1, A2J2 up to ASJS up to ANJN, and of course that's a typo because as long as I'm not in row S, BNJN is ANJN. Okay. Obviously I need more space, so we'll come to the top. Now, in this first sum, I can pull the C in front. So I get C times the summation plus minus of A1, J1, A2, J2. Now, remember, somewhere I said R is less than S. All the way up to ARJS, all the way up to ASJS, all the way up to A sub n, J sub n. And for completeness, plus the second summation, the summation plus minus A1, J1, all the way up to AN, JN. Okay. Well, that second summation, that's just a definition of the determinant of A. Now, for this theorem to be valid, I just need to argue why this is 0. I need to argue why this is 0. Okay. Okay, now, I'm just slightly troubled by that. Now I understand why. Okay. Let's look down here and remember that R is less than S. R is less than S. That is, somewhere in here, you're going to have ASJS. Oh, and that is what I did. After this, I put that. Okay. Now I even have problems with the second summation. All right. So I even have problems with the second summation that I wrote down. And now I'm really getting confused. Oops. Can't hold them off. They're in my hand. All right. So we have the second summation when we're using this term. Now remember, here is ASJS. So basically we have A1J1, A2J2. Eventually we have ASJS. And then somewhere else we have ASJS. And then eventually ANJN. Okay. I just want to make sure that those column entries are going to be correct. Just want to make sure that those column entries are correct. So I agree that this is BSJS, so the column is J, and that's what I put, column J. So that's correct. Now, what I want to say, and this is what's confusing me, I want to say now that this second sum is 0. I want to say that this sum is 0 because it has two rows that are exactly the same. The auth, the JS column, those are the same. So, and every time we sum up, so what would the matrix look like? What would the matrix look like? Okay, for one of them is, this top one, I'm not seeing it for some reason. This top one is 0, and this bottom one is a determinant of A. And when you add 0 and a determinant of A, you get the determinant of A. Okay? Try to clean it up. I'm sorry I'm not seeing it at the moment. Let us verify this theorem by looking at a couple of examples. And to be honest, before you look at these examples, you should really try to write up the proof. you think about it perfectly, you have the greatest command of what is going on, you will see how to put it together. So suppose we have matrix A. Matrix A is 1, 2, 3, 5, 1, 3, 1, 4, 5. And I want to double this row and add it to that. That is, row 2 is going to be, row 1 is going to become 2 row 2's and then add row 1 to it. And that's how matrix B is going to be defined. The second and third row does not change. But for the first row, I'm going to add 2 times the second. 2 times this is 10, plus 1 more is 11. 2 times this is 2, plus 2 is 4. 2 times 3 is 6, plus 3 more is 9. I claim that these two matrices should and will have the same determinant. The determinant of A is a matter of just using what I call the spaghetti method on these, 15 numbers. This product is 5, this product is 6, the next product is 60, minus this product is 3, the next product, that one is 12, this one is 50. And, if that number was 60, I would definitely cross off the 60s. But you know what? I hate big numbers. 60 minus 50 is 10. 11 plus 10 is 21. Minus 15. I get 6. How you do arithmetic is up to you. I'm not going to teach you how to do arithmetic. Matrix B, determinant of B. 11, 4, 9, 5, 1, 3, 1, 4, 5, 11, 4, 5, 1, 1, 4. It's going to be that product, which is 55, plus that product, which is 12. 20 times 9 is 180, minus this product, which is 9. 12 times 11, you should know. 25 times 4 is 100. 100. Okay. 180 minus 100 is 80. 67 and 80 is 147 minus 141. 6. Look at that. Same answers. They give the same answer. You can add a multiple of one row to another row. Now, you cannot add a multiple of one row to a multiple of another row and say the determinants are the same. Because when you multiply one row by some number, and you replace that row with that multiple, that's different. If you multiply a given row by 7, and you put that result in that row, that's different. In other words, 1, 2, 3, 4, 5, 6, 7, 1, 2. If you multiply row 2 by 2, you multiply row 2 by 2, these determinants, or these matrices, will not have the same determinants. the determinant of A is not the determinant of B, but rather the determinant of B is, I multiplied row 2 by 2, is 2 times the determinant of A. Okay, but now here's something different. It's going to sound almost the same. It's going to sound almost the same. I am going to get B, I'm going to multiply this row by 2. And if I stop there, that's exactly what I said up here. I'm going to multiply row 2 by 2 and add that to A. Add that to row 1. That changes things. I get 9, 12, and 15. I added a multiple of row 2 to row 1. I did something with that multiple other than keep it where it is. From in the top A to B, I multiplied row 2 by 2, and I replaced that result, 8, 10, 12, with row 2. I replaced row 2 with that result. But what I'm doing on the bottom is I am multiplying row 2 by something. But notice, row 2 didn't change in B. Why? Because what did I do with that multiple of row 2? I added it to A. The determinant of A and the determinant of B are equal. You can't multiply row 2 by 2 and then add it to itself. If you did, you'd have 3 times row 2. So the determinant of that new matrix will be 3 times the determinant of the old matrix. You have to add the multiple to another row. You can't even add it to a multiple of another row and get back the same determinant. Okay, think about this. All right. Here's an interesting theorem. And boy, does it make life easier if you know this. If A is upper or lower triangular, then the determinant of A is just a product of the entries on the diagonal. A11 times A22 times A33 up to times A and N. Not going to prove this. Example. If A is equal to 1, 2, let's make it more interesting. 4, 2, 1, 0, 5, 3, 0, 0, 7. Notice everything below the diagonal is 0. You could immediately say the determinant of A is a product of those 4 numbers on the diagonal. 20 times 7 or 140. If it's lower triangular, that is everything above the diagonal is 0. 3, 0, 0, 0. 2, 2, 0, 0, 4, 3, 2, 0, 0, 1, 2, 5, negative 5. There's a diagonal, and everything, in this case, above it, up here, is zeros. Oh, so the determinant of A is simply a product of the numbers on the diagonal. 6 times 10, 60. 3 times 2 is 6, times 10 is 60. In our case, negative 60. So that really makes life easier. If you have an upper or lower triangular matrix to determine, and it's, well, it has to be square. then the determinant is easily obtainable. Just multiply the numbers on the diagonal. You know, back in elementary school, maybe your teacher would ask you to multiply those three numbers. Well, now, in linear algebra, your teacher is completely off the wall, has no idea how to think anymore, and instead of asking you to multiply those three numbers that way, now says, calculate that. Calculate this determinant. Well, they're just asking you what 2 times 5 times 4 is. Just another way of saying the same thing. Oh, my teacher's just asking me what 2 times 5 times 4 is. Yeah. And a little bit more, your teacher's asking you to know that if it's upper triangular, then the determinant is a product of the diagonal entries. So know that. Okay, know that. That really makes life easier. You don't want to spend time on an exam trying to find the determinant of a upper triangular matrix by the spaghetti method. Okay, you don't want to do that. It just takes a bit of time. And why would you want to spend time when you don't have to? Okay, you need to know all the tricks to save time. Here's this theorem that I'll just state. If A and B are square n by n matrices, instead of multiplying A and B first and then taking the determinant, you can take the determinant of A and the determinant of B and then multiply. That is, the determinant of a product is the product of these things which are determinants. The determinant of a product is the product of the determinants. Determinant of AB equals the determinant of A times the determinant of B. So, for example, if you were told A is equal to 1, 3, 4, 2, and matrix B is, I don't know, 3, 1, 4, 5, and you compute the product 1, 3, 4, 2, 3, 1, 4, 5, you're going to get 15, and one more 16, and then I guess 20, and then 14. Okay. Now, check this out. The determinant of A, well there, it's easy. 1 times 2 is 2, minus 12, it's negative 10. 12 came from 4 times 3. The determinant of B is 3 times 5 minus 4 times 1, it's 11. Okay. Now, the determinant of this matrix, I don't care what they call the matrix. They want to call it AB instead of just A or just B or just C. I'm not going to panic. I mean, after all, it looks just like a matrix normally does. Multiply those two numbers, 14 times 15, 210, minus that product is 320, and this is negative 110. And you know what? Negative 110 is negative 10 times 11. And negative 10 is, look at there, oops, look here, determinant of A, and 11, the determinant of B. That is, the determinant of AB really is the determinant of A times the determinant of b. It really works. Okay, you can do 10, 20 examples, but they're just examples of taking determinants. Find the determinant of a, hold on to it. Find the determinant of b, hold on to it. Calculate 8 times b, and then calculate its determinant. And say, oh yeah, look at this. The determinant of this matrix AB really does equal to what I calculated the determinant of A to B times the determinant of B. See now, if you're told the determinant of A is 3 and the determinant of B is 4, well then the determinant of AB, well, we know that that theorem says it's this, and you say, oh, they told me that's 3. Oh, they told me that's 4. 3 times 4 is 12. Know the theorem. A lot of these theorems don't say much. The determinant of A equals the determinant of A transpose, the determinant of AB, the determinant of A times the determinant of B. They're not hard theorems to state, but you have to remember them. And they're not even hard to use, but you have to remember them. Okay, now here's a corollary to our last theorem. If A is non-singular, that is, it has an inverse, two things we can say. Then the determinant of A is not 0, and the determinant of A inverse is 1 over the determinant of A. Now, for the proof, the first thing I'll notice is, you know what, this is a strange way of saying this. I would tend to think of that up there. And that's where it all comes together. That is where it all comes together. On one hand, the determinant, so we are told that A is non-singular. Hence, it has an inverse. I know the determinant of I is 1. Why? Because I is a upper, or if you prefer, lower triangular matrix. So the determinant is the product of the numbers on the diagonal. This matrix on the bottom I just wrote is lower triangular because everything above the diagonal is 0. You want to say, oh, everything below the diagonal is 0, so it's an upper triangular matrix? Fine. Say one or the other. And then you say, oh, the determinant is just the product. So that's another theorem. The determinant of the identity matrix is always 1. But you know what? I is the same as A times A inverse. That's I. But I don't want I want the determinant of I. And then it all comes together. This is the determinant of A times the determinant of A inverse. Now, these are real numbers. If I told you x times y is equal to 1, wouldn't you guarantee me that that's not 0? Okay, so let's write that down. So, the determinant of A times the determinant of A inverse is 1. Well, that implies that the determinant of A is not 0. Because if this is 0, and it's a real number, what on earth are you multiplying it by to get 1? Okay, well, if I divide both sides by the non-zero number, determinant of A, I get that. The determinant of A inverse is just the reciprocal of the determinant of A. Of course, the determinant of A is 1 over the determinant of A inverse. Okay. And this is all you need for your proof. In fact, there's the proof right there. The product equals a non-zero number. Then the things that are multiplying to make up this product, none of them are zero. Okay, you have to have that fact, not only know it. Oh, yeah, of course. You're not telling me anything that I didn't know. Fine, but you have to be able to know when to use it. If I give you a product that equals 1 or equals to 0.093 or it equals to the square root of 11, you have to say, oh, none of the things you are multiplying, which are called factors, none of the factors are zero. Nothing amazing there. Nothing at all amazing there. Okay, so if I tell you A is non-singular, and I tell you the determinant of A is 1/4, that implies the determinant of A inverse is the reciprocal. If I tell you the determinant of A is 3, that implies the determinant of A inverse is 1/3. If I tell you the determinant of A inverse is 2/3, that implies the determinant of A is the reciprocal. The determinant of A is 1/, the determinant of A inverse. If two quantities are equal, then their reciprocals are equal. That implies the determinant of A is 3/2. They're reciprocals. The determinant of A is equal to 9. That implies the determinant of A inverse is 9, which is 9/1. That implies the determinant of A is 1/9. Now, remember, the determinant, A is non-singular. Well, look what we proved. We proved the determinant of A is not 0. So if A has an inverse, then the determinant of A is not 0. Now, does the implication go the other way? If the determinant of A is not 0, well, I don't think so. Because just because the determinant of A is not 0 doesn't guarantee us the existence of the determinant of A inverse. Just because the determinant of A is not 0 does not guarantee us that A has an inverse. It does, but not from this theorem. Not from this theorem. A little bit later on, we'll make that statement. And then we can add the fact that the determinant of A is not equal to 0 to our list of non-singular equivalences. So how about A and B are n by n matrices? A and B are n by n matrices. The determinant of A is 3. The determinant of B is -5. And let me state it. A and B are square matrices of the same size. Remember, if I don't say they're n by n, I just say they're square. A can be 3 by 3. B can be 5 by 5, and we can't talk about A times B because coincidentally, that says 3 and that says 5. But if a is 3 by 3, and we try to multiply it by 5, this does not exist for the simple reason, way back from the beginning, the inner numbers are not the same. So, what if you wanted to calculate the determinant of A transpose B inverse? Suppose you wanted to calculate that determinant given the information I wrote above. Given the information I wrote above, we want to calculate that. And the way to do such a problem is to know the theorems. If you know the theorems, this is quite easy. We have a product. One matrix is A transpose, one matrix is B inverse. But nonetheless, we're multiplying them, and we want the determinant. Well, first thing I would say is, well, I only know about determinant of A and determinant of B. Let me break this up. Determinant of A transpose times the determinant of B inverse. At least now I have A and B separate. And then you say, oh, yeah. The determinant of A transpose is just the determinant of A, which is good. I know that. Oh, the determinant of B inverse is 1 over the determinant of B. Our last theorem. The determinant of A is 3 times 1 over. The determinant of B is negative 5. You get 3 over negative 5, which is negative 3/5. Pretty neat. We were able to calculate the determinant of A transpose times B inverse, and we didn't know the determinant of A transpose. We weren't given the determinant of A transpose, nor the determinant of our B inverse. Now, what if we wanted the determinant of A cubed? Now, you just can't randomly guess and say, oh, this must be the determinant of A cubed. That is, the answer is 3 cubed. Hey, maybe yes, maybe not. Now, we only know the determinant of A. And we have some theorems that we can use. So somehow, I want to get A cubed to have A. And take the determinant of that. A cubed is A times A squared. So at least now I have the determinant of A times the determinant of A transpose. Sorry, A squared. Now you don't need to put these brackets, but let's put those brackets here anyways. So the first one is the determinant of A times, now A squared is A times A. Oh, look at that. Here's the determinant of A that's in front, and the determinant of A times A, determinant of a product, I can multiply the determinants together, and yeah, this is the determinant of A cubed. And the determinant of A is 3, and I cube it, and I get 27. But you can't just jump there. Now, I'm not saying you had to write all of this. If you can see what I just circled in your head, that's fine by me. Jump right there. Of course, on a test, if your teacher wants you to show the work, you needed to do this. You don't have to show the obvious things, but that you'd have to show. And this disturbs me with how some teachers teach their classes. 2 times WAD equals 10. Let's write it a bit clearer. Two times x equals 10. 2 times WAD equals 10. Well, I think little Johnny should know that. 2 times what equals 10? Should know that. Okay, and if you just wrote the answer down, teachers mark you wrong. You didn't show your work. Well, let's do it the way they want you to do it. Divide both sides by 2, and then say x is 5. Well, wait a moment. Why is that 5? Teacher's responses, I would suspect, would be, you should know it. You should know what 10 over 2 is. Well, then you should know. So why not know that 2 times 5 equals 10? Okay, you showed all your work. You showed all your work here. But in that last problem, you can't say that the determinant of a cubed is the determinant of a all cubed. That is pushing it. Besides, you don't even know if it's really true. If you see that in your head, well, let the teacher know what you're seeing. Let the teacher know what you're thinking every step of the way. Like 2 times what equals 10? What equals 5? You have 2x plus 3, 25. There's no reason why you shouldn't know that's 22. So write it down. That is 22. That's the first thing you observe. That's 22. You wrote it down. I showed my work. 2 times what is 22? Oh, the what must be 11. There's absolutely nothing that I didn't show. Okay? You should know 22 plus 3 is 25. And if you don't know, go and thank your teacher. Not me, please. My students are supposed to know that. Okay, thank your teachers for not asking you to think. Okay, now that I'm going off on this, I was highly insulted. You know, people who, most kids, 5 years old, 4 years old, 2 maybe, they know that 1 plus 1 is 2. Well, I was very upset. I didn't speak out, but I was very upset that my algebra teacher, they didn't just say, well, class, you know, x is 1. 1 plus 1 is 2. She goes, no, you have to take away 1 from both sides. Nonsense. Think. Stop doing things mechanically. Okay. Let's move on to some theoretical exercises. One can argue that the last 2 were. Okay, so we want to show that if C is a real number, a scalar, and A is an n by n matrix, then the determinant of C times A will be C to the n times the determinant of A. Now, remember, if you had A, and its determinant is the determinant of A. If you have A, and you multiplied row R by C, and you got B, you multiply just 1 row of A by R, by C. So let me say it again. You have matrix A, you take 1 row, row R. You multiply straight across by C. Well, then the determinant of B would be C times the determinant of A. And then if you take B and you change, well, let's suppose you multiplied row 1 by C. And that gives you matrix B1. And then you take B1 and you multiply the second row by C. And then you take and call that matrix B2. So, and then you do the same to the third row, to the fourth row, etc. Every time you multiply one row by C, the new determinant, the determinant of that new matrix is now C times larger. It's multiplied by a factor of C. Okay, so we're going to do this proof, some multi-step proof, but each step is the same argument. You're just going to multiply a different row. Okay, proof. B1 is obtained from A by multiplying row 1 of A by C. Okay? The determinant of B1 is not determinant of A, but C times the determinant of A. Okay? B2 is obtained from B1. So B1 is not A anymore. It's A, but the first row is multiplied by C. B1 is obtained from A by B1. Okay, let me slow it down. B2 is obtained from B1 by multiplying row 2 of B1 by C. So the determinant of B2 is C times the determinant of B1. But the determinant of B1 is C times the determinant of A. So it's C times what that is. But that's C times the determinant of A, which is C squared times the determinant of A. Do it again. B3 is obtained from B2 by multiplying row 3 of B2 by C. So the determinant of B3 is C times the determinant of B2. It's C times that. But the determinant of B2 is C squared times the determinant of A, which is C times C squared is C cubed times the determinant of A. Continuing, we get to Bn. Bn is the last row. Remember, B1 affects row 1. B2 affected row 2. B3 affected row 3 by multiplying row 3 by C. And Bn affects the last row. This is going to be Cn, the determinant of A. So we're just doing it we're doing it row by row. Oh, this theorem says we can only multiply one row by C, one default. I'll do that n times. Oh, you mean that's what I get? So now, what if you multiply 5 rows by C? You take matrix A, you randomly pick 5 rows. Let's work with me, folks. A has at least 5 rows. Okay, A is n by n. N is at least 5. A is n by n. N is 5 or bigger. Pick any distinct 5 rows of A and multiply these rows by C. Call this new matrix B. Now when I say distinct 5 rows, that means you can't pick row 1, row 2, row 4, row 2, and row 6. They're not. They all have to be different. That's all that means. Pick any different 5 rows of A and multiply these rows by C. Call this new matrix B. How do you compare the determinant of A and the determinant of B? Then the determinant of B will be C to the 5th times the determinant of A. Okay, every time, say, maybe you multiply, R3 and then R2 and then R5 and then R1 and R7. Let me put R7 here. Well, when you multiply the third row by C, call that matrix B1. And the determinant of B1 will be C times the determinant of A. And now you multiply row 2 by C. Call that matrix, you multiply B1, the row 2 and B1 by C, and now you get B2. Well, that's going to be B times C times the previous one. It's going to be C squared A. Okay, just think about it. By the time you get to the 5th matrix, by the time you multiply 5 rows by C, you're going to get that. Now, if you multiplied row 1 by A, one row by A, another row by B, another row by C, another row by D, and another row by E, the determinant of this new matrix will be A, B, C, D times the determinant of the original matrix. And I'm going to make one change. You most definitely can pick row 2 twice. Okay? Maybe by the time you get up to here, you have C 3 times the determinant of A. If you multiply row 2 again, after multiplying row 2 by C, you multiply it again by C, well then you're going to get C to the 4th times the determinant of A. So they don't even have to be distinct. Was I wrong when I wrote distinct? No. If they are distinct, it works. If they're not distinct, they work. But it's stronger. I mean, you want to have a more general theorem. And the one that says they don't have to be distinct is more general. Right. Show that if A times B is the identity matrix, then the determinant of A is not 0, and the determinant of B is not 0. The determinant of IN is 1. But In, they told me, is AB. They said it. In and AB are the same. So they have the same determinant. And the determinant of AB is the determinant of A times the determinant of B. And we've already talked about this. But now I'm going to talk about both matrices at the same time. If you multiply two real numbers and you don't get 0, I don't care if you get 1 or 17, if you don't get 0, neither of those factors is 0. Since the determinant of A times the determinant of B is 1, which is not 0, that implies that determinant of A is not 0, and the determinant of B is not 0. You can't multiply two numbers and get 0 and get 1 if one of those numbers is 0. Okay. Some matrices equal its own inverse. Some matrices are their own inverse. And think about the identity matrix. Let's see what would have to be true for that. Let's look at 2 by 2. Let's multiply a matrix by itself. And we get A squared plus BC, AB plus BD, AC plus CD, and BC plus D squared. And we want this to be the identity matrix. That is, this should be 1, these two should be 1, and the other two should be 0. A squared plus B times C should be 1. BC plus D squared should be 1. And here I'm going to factor out the B. B times A plus D should be 0. And here I'll factor out the C. C times A plus D should be 0. Now, in this one, if I subtract, the BC's cancel out. So A squared minus B squared should be 0. But that's A plus D times A minus D should be 0. That is either A plus D is 0 or A minus D is 0. Okay, so let's write that down here. A plus D times A minus D is 0. I need these three to be valid at the same time. You know what? They all have the same factor, A plus D. So as long as we let A plus D equal 0, that is, A is negative D, I think, it's hard to believe, but I think a matrix will always be its own inverse. If these differ by signs, like 2, 3, 4, negative 2. 1 minus 1 is 0. Okay, this should be its own inverse. That is quite surprising to me. Yeah, I didn't think that would work. Well, that's definitely one of their conditions. Okay. So, let's look at this. If I factor out, I get B times A plus D, And over here I get C times A plus B. C times A plus B. And I want those two entries to be 0. Well, if A is negative B, we're okay. Now, we have to work on these entries being 0. Okay, so let's see what has to be true about the other variables for those entries to be 0. Let's get our hands dirty. If A is negative B, that says that B squared plus BC should be 1. And this says that BC plus B squared should be 1. Okay, so we need that to be true. We need that to be true. So, can you think of two different numbers that multiply out to something squared? Here. 8 times 2. Let this be negative 8. So B is negative 8 and C is 2. So this is negative 16. And I will let D be 4. So 4 squared is positive 16. And A must be a sign change from that. So there it is. A is negative 4, B is negative 8, C is 2, and D is 4. Oh, no. I want to get 1, excuse me. I don't want to get 0, I want to get 1. Which I think makes life a little bit easier. This is going to make life a little bit easier because I see the answer right away. If I let D equal 5, then that will be 25. Now, I want BC to be negative 24, because negative 24 plus 25 is 1. So B will be 6, and C will be negative 4, and A, according to what's up here, A and D differ by signs. Now I'm happier. Okay, here is a matrix. I'm hoping that is its own inverse. A, B, C, and D. A, B, C, and D. When I multiply this, I get 1 here, and 0 here, and 0 here, and 1 here. I get their identity. That is, if this is A, it's its own inverse. Okay. So I found two matrices. I found a matrix that when I multiply it by itself gives me the identity matrix. That is, this matrix is its own inverse. And don't randomly put down matrices and multiply them by themselves until you get the identity. Try to figure out what has to be true. Okay. Now, let's calculate the determinant of A. It's this product, which is negative 25, minus this product, which is negative 24, and I get negative 1. The determinant of A is negative 1. Now, I don't see why this wouldn't work. Of course this will work. This matrix times itself is also the identity. Now, what I did was, is I took this product and I multiplied it by 1. I multiplied it by negative 1 times negative 1. And then I scaled, or I scalar multiplied each matrix by negative 1, and I got these two matrices. This is also the identity. We'll call this B, okay? The determinant of B is this product, which is negative 25, minus this product, which is negative 24. Which is also negative 1. So what we're going to do is we're going to interchange the two rows, because I know one of my theorems tells me if I interchange two rows, the determinant will change the sign. Boy, I don't see it. But all right, the bottom line is we got negative 1. The determinants were negative 1. The determinant is negative 1. Apparently, when you interchange the two rows, you're not going to get the identity matrix. The theorem says the following. If A equals A inverse, then the determinant of A is either plus or minus 1. We did get minus 1. Let's convince ourselves that it can be 1. Wow, I see determinants, and I see 1, and I see A and A inverses. I jump to the identity. I just see that there's a really, really good chance that this is going to work if I deal with identity. The determinant of the identity matrix is 1. But the identity matrix is A times A inverse. So that's the determinant of the identity matrix. But A inverse is A. So I'm going to replace A inverse with A. So this is the determinant of A times A. But we did this one earlier. Remember, the determinant of A to the n, we really only did it up to 3, is the determinant of A to the n. And if you don't want to do that, you can say this is the determinant of A times the determinant of A, and then say it's the determinant of A squared. The determinant of A squared is 1. If something squared equals 1, then that something is plus or minus 1. To try to find a matrix that has two properties. The determinant is 1, not negative 1, it's 1, and it's its own inverse. And then after you see why my example gave me negative 1 and why your example gives you positive 1, you'll be able to figure out what answer you're going to get before you even work it out. There's reasons why my matrix had a determinant of negative 1, and when you squared it, you got identity. And there's a slightly different reason why your matrix has a determinant of 1, and when you square it, gives you identity. Just figure out what that change needs to be. Maybe I needed to change the columns, multiply a column by negative 1. Maybe that would have done it. Okay, very similar problem. Now, these theorems, you don't have to walk around knowing. Okay? It's good if you know them, but you don't have to. If A transpose is A inverse, then the determinant of A, once again, is plus or minus 1. When I see inverses of A and A, I mean, here's inverses, here's A, and determinants, and you're getting 1, I think of identity. 1 is equal to their determinant of the identity, which is the determinant of anything that equals to the identity. Well, before you can talk about A inverse, there must be a matrix A for A inverse to be the inverse of. That is, A and A inverse do exist. So this becomes the determinant of A. Times the determinant of A inverse. I understand now. Okay. In this problem, A inverse is a transpose. But always, a determinant of A transpose is a determinant of A. So we have the determinant of A squared. And that equals 1. Well, that implies that the determinant of A equals to plus or minus 1. Determinant of A is plus or minus 1. Okay, couple more theorems and we'll be done. Okay. Show that if A is a non-singular matrix such that A squared is equal to A, then the determinant of A is identically 1. Okay. And the proof is as follows. At least this is how I would lean towards doing this. We'll see if I get burnt enough. I don't like that we have A squared. We've done a few of these, and possibly if I didn't do a few of these, I might not make this statement. Probably would, but the fact is we've done a few of these, and we never had A squared. Determinant, we want to show it's 1, and it's invertible. It has an inverse. A has an inverse. So remember, A squared means A times A. And that equals A. Well, on the left side, I'm going to multiply by A inverse. And then I use associative law. I have A inverse A. I'll bracket it this way. And I'll leave it as A inverse A for now. This is identity times A, and that's the identity. Identity times A is A. that A is the identity. There's only one way A squared. If you square a matrix and you get yourself back, well, that's not true. If you square a non-singular matrix and you get back the matrix you started with, it had to be the identity. So the determinant of A is equal to the determinant of I. And the determinant of A, we don't know, so we think, but we know the determinant of I is 1. Well, that's what I wanted to show. If A is non-singular, if A has an inverse, and A squared equals A, there's only one way that can be. The only way a matrix multiplied by itself to give you back A, if the inverse exists of this matrix, is if the matrix is the identity. A must be the identity. You want to go from here to there? Fine. It's not unreasonable for you to know if A is the identity matrix, then the determinant of A is 1. You should definitely think. Okay. Show that the determinant of A transpose B transpose is equal to the determinant of A times the determinant of B transpose, which equals the determinant of A times the determinant of B. These two look very similar. So you probably want to show that this one equals that, and that it also equals this one. Again, if you want to show 1 equals 2 equals 3, there's many ways of doing this. You can show 1 equals 2, and you can show 1 equals 3. So if 1 equals to both of these, then those two are equal. So you can show 1 equals 2, and then you can show that 2 equals 3. That is 2 equals 1 and 2 equals 3. So 1 equals 3. They're all equal. You can show that 3 is 1 and 3 is 2. So then they're all 3 equal. All right, proof. The determinant of A transpose B transpose is the determinant of A transpose times the determinant of B transpose. And I'll just do it here. The determinant of A transpose is the determinant of A. I will not change the determinant of B transpose. The determinant of A transpose, I'm not changing. Times the determinant of B transpose, well, that's just the determinant of B. And I proved both of these. I proved both of them. Not a very long proof. Definitely a proof that you should be able to do on a test. Personally, I don't think I would give that one because it's a bit simple. Okay. We'll finish up this section by doing this last proof. Show that if A is non-singular, is a non-singular matrix. Oh, I'm sorry. Thinking of the wrong one. show that if a to the n equals 0 for some positive integer, n, what should be true? Here, the determinant of a should be 0. So we're going to assume, there's two things that we could assume. We could assume the determinant of a is 0, or the determinant of a is not 0. If we assume the determinant of a is 0, we're done. Why? Because the determinant of a is not 0. So proof. Assume the determinant of a is not 0. Is not 0. Okay, so the determinant of an is 0, but that's the same as the determinant of a times the determinant the determinant of a times a to the n minus 1. But this is the determinant of a times the determinant of a to the n minus 1. Now, these are real numbers, like 7 and 4. Their product is 0. And we're assuming that the determinant of a is not 0. Well, that implies that the determinant of a to the n minus 1 must be 0. Okay? So, 0 is the determinant of a to the n minus 1. But a to the n minus 1 is a times a to the n minus 2. I'm multiplying two matrices and taking the determinant of it. I could take the determinant separately and multiply. That is, it's the determinant of a times the determinant of a to the n minus 2. And it equals 0. The product equals 0. But this first one, determinant of a, we're assuming is not 0. So then that must be 0. That implies the determinant of a to the n minus 2 is 0. Continuing in this fashion, notice the powers going down. First, the determinant of a to the n was 0. Then the determinant of a to the n minus 1 is 0. And then the determinant of a to the n minus 2 is 0. Eventually, we'll get to the determinant, say, of a cubed is 0. Now, you can say we already proved that means the determinant of a is 0. But if you want to continue, this is a cubed is a times a squared. So this is the determinant of a times the determinant of a squared. Since this is not 0, this must be 0. So the determinant of a squared is 0, which is the determinant of a times the determinant of a, which for the record is the determinant of a squared. Well, if you square something, I don't care what you're calling a something, if you square something and you get 0, that's because that something is 0. Okay. Now, another way to prove this, is to prove that the determinant of a to the n, to prove that the determinant of a to the n is the determinant of a to the n. Now, once you have that, if this is 0, then you can say immediately, the only thing you can raise to the 12th power or the 25th power or some positive integer power is, and get 0, is 0. But it would have been a lot of work, as much as we've done maybe, if not more, to prove this. But once you prove this, once you prove that the determinant of a to the nth power is equal to the determinant of a to the nth power, then it's, this much to finish the proof. That completes this section on determinants. It was a long one, wasn't it?